So we are going to talk about a secret stack pattern. So have you ever got stuck writing nested loops just to find the next greater element in an array? So brute forcing would take brute forcing would take big O of n square time because every element has to look ahead through the rest of the array. I'll tell you how. Let's see. We have a person standing here, and that person has to find the next greater element to this building. Let's say this is a building and all of these are buildings of different heights. So that person will go to next building, check if it is greater. If no, it will go to the next building, see if it is greater. If yes, it will then come back here, tell the next greater building to this is this, and then move forward and come here, find the next greater element for this building by iterating through the rest of the array. So this takes big O of n square time, right? But what if we could optimize this into linear time? Let's see how do we do that. So in order to do that, we would use this waiting room thing. So what do? We keep a waiting room of elements that haven't found their answer yet and resolve them instantly the moment a larger number appears. So in our case, what is this waiting room? It's a stack, right? So each element will wait until it has got its answer. So in our stack currently, we have 2 and 1. And then 5 arrives. So now, since we're solving next greater element question, now since 1 is pop 1, why? Because 5 is greater than 1, and we are also going to pop 2. Why? Because 5 is greater than 2. So we have found the next greater element for multiple elements in the waiting room or the stack, right? So that's why one arrival resolves multiple waiting elements. So before diving into the monotonic ordering, recall how standard stack operate. In like lead code 20, valid parenthesis question, the stack enforces matching order by pairing closing brackets with the most recently pushed open bracket. And in lead code 150, reverse polish notation, the stack acts as a temporary memory or a waiting room, holding operands until an operator comes and consumes the top 2 elements. So the key in both cases is last in, first out, or the LIFO principle that we already know. So we need to process data sequentially without needing to rescan previous elements. And coming to the monotonic stack shift question, we have the same stack, but with a strict rule added to it. And the strict rule is we have to maintain order inside the container or the stack. So as we iterate through the array, we have to have a waiting room. We can either have it in a increasing order or decreasing order, the waiting room. And then when a new value breaks the order, we have to pop until the order is restored again. And the order will tell you exactly which unresolved elements are now answered. So let's see how. So let's walk through the example 2 and 5. Now let's see. See, we have a number 2 in our array. So now what we are going to do, we have to add 2 to the waiting room or a stack. Now 1 arrives. Well, I mean, we scan 1 in the array. Then we add 1 to the stack. We are solving next greater element. So our stack is currently in decreasing order, right? 2, 1. Now what happens? 5, we scan 5. Can we push 5 to the stack? Not really. Why? Because, I mean, 5 is not less than 1, right? Since 5 is greater than 1, we have to pop 1. Now, since we have popped 1, we know the next greater element for 1, which is 5. Now, again, we need to, 5 is greater than 2, so we can't push 5 right now. So then we have to pop 2. And that's when we know we have found our answer. So, because every element enters and leaves the stack at most once, total time complexity drops from big O of n squared to big O of n whenever a problem asks for next greater, previous smaller, or building area boundaries like lead code 155, minimum stack variation. We can skip the nested loops and reach for a monotonic stack. And I have, if you want more detailed video explanations on any of the questions, I have attached the links to those videos in my description. Thanks for watching. Bye.